निर्माण नो अभिगम कल्याण हो छात्र नो हरदम उच्च अभ्यास नो शिक्षण धाम महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल.
Today we will be studying chapter 1, real numbers, introduction and solution to exercise 1.4, where we would be revisiting rational numbers and their decimal expansions. In our previous classes, we had learned regarding irrational numbers, rational numbers also we had discussed, and we had also discussed this together rational numbers and irrational numbers gives us real numbers. That is what we are talking about. Moving on to our present exercise, rational numbers. What are rational numbers? We had gone through various definitions regarding rational numbers in our previous classes. Let us revise it once again. Those numbers which can be expressed in P upon Q form, where P and Q are co-prime numbers and Q is not equals to 0, were considered to be the rational numbers. Talking regarding the decimal expansion, if in the decimal expansion of a particular number the remainder becomes 0, that means the decimal expansion of a particular number terminates, then also we consider such number to be a rational number. If the decimal expansion does not terminate, then there is a repetition of digits, single digit, 2 digits, 3 digits, or more than 3 digits in the decimal expansion of that number, then such number are also considered to be rational numbers. That means a non-terminating yet repeating. The repetition should be in a pattern. Non-terminating and repeating decimal expansions are also considered to be rational numbers. But every time we need to divide to check whether it is a terminating decimal expansion or non-terminating decimal expansion. Without dividing also, we can know whether a given particular rational number is a terminating or non-terminating. If it is non-terminating, then there might be some conditions for it to be repeating. That is our main topic for today. How would we be identifying a particular rational number to be terminating or non-terminating? Moving on to that, let us move to our first theorem, that is theorem 1.5 from NCERT. Let x be a rational number. That means x is a rational number whose decimal expansion terminates, means it's a terminating decimal expansion. Then x can be expressed in P upon Q form, where P and Q are co-prime numbers and the prime factorization of the Q is of the form 2 to the power n, 5 to the power m, where n and m are non-negative integers. Let us move slowly. Let x be a rational number whose decimal expansion terminates. That means we need such a decimal expansion that is terminated one, and that would be a rational number. Let us take an example. 0.56. Suppose this is our rational number that is a terminating decimal expansion. If it is a terminating decimal expansion, then x can be expressed in P upon Q form, where P and Q are co-prime numbers. That means this rational number that is a terminating decimal expansion can be expressed in P upon Q form. How? Let us see. If we remove the decimal part, it becomes 56 by 100. If you simplify it, then you get 28, then 50, then 14 and 25, then 7 and then sorry 28, 14 and 25. No, it cannot be cancelled. Now we can write this one as 14 upon 25. 0.56, a terminating decimal expansion being a rational number, can be expressed in P upon Q form as 14 upon 25. So, moving on to again our theorem, let x be a rational number whose decimal expansion terminates that we have taken, then x can be expressed in P by Q form that we have expressed it, where P and Q are co-primes, that too we have expressed it, and the prime factorization of Q. Q means this is my Q and this is my P. And the prime factorization of Q is of the form 2 to the power n, 5 to the power m, where n and m are non-negative numbers. Non-negative numbers means all the positive numbers along with 0. So this can be written as 14 upon 5 to the power 2, 2 to the power 0, where n is 0 in comparison to us, n is 0 and m is 2, and m and n both are non-negative integers. So we can express a terminating decimal expansion in the form of P by Q with the condition that Q will be of the form 5 to the power 2, 2 to the power 0, that is 5 to the power m into 2 to the power n. That means a terminating decimal expansion can always be expressed in this form, denominator being of the form 2 to the power n and 5 to the power n. Moving on to our next theorem, let x is equals to P by Q be a rational number such that the prime factorization of Q is of the form 2 to the power n, 5 to the power n. Now we are given with a rational number that is in the form of P by Q, and Q should be of the form 2 to the power n, 5 to the power m, where n and m are non-negative integers. So let us take a rational number in example, say 7 upon 2 to the power 2, 5 to the power 3. Now let us move on slowly. X is equals to P by Q. We have got x is equals to P by Q such that prime factorization of the Q is of the form 2 to the power n, 5 to the power n. The prime factorization form of the denominator, that is Q, is of the form 2 to the power n, 5 to the power m. Then x has a decimal expansion that terminates. That means if we divide the numerator by the denominator, it will terminate. That means if the denominator is of the form, always of the form 2 to the power n, 5 to the power n, the total decimal expansion of that rational number will terminate. That means remainder will become 0. If you have other numbers attached to these two forms, 2 to the power 2, 5 to the power 3, and there is another number, any number, you can say any prime number, 3, 5, 7, 13, whatever number is attached with it, then this will not terminate. The denominators should always have 2 and 5. Along with it, it should not have any other prime number. The denominator should be completely of the form 2 to the power n, 5 to the power m. Next theorem, theorem 1.7. Let x is equals to P by Q be a rational number. Then the prime factorization of Q is not of the form 2 to the power n, 5 to the power n that we were talking in the previous theorem. Say an example, we are given with 7 by 2 to the power 2, 5 to the power 3, and there is an extra prime number, say 13 to the power 2. Now this is a rational number which is in the form of P by Q. The Q is not in the form of 2 to the power n, 5 to the power m, because there is an extra 13 to the power n, a prime number with a degree. In such a case, Then x will have a decimal expansion that is non-terminating and repeating. That means if we divide the numerator by the denominator, it will be a non-terminating decimal expansion, but there will be repetition of digits in a specific pattern in the decimal expansion of p by q. Such a case is also very applicable to find that whether a decimal expansion is a terminating decimal expansion or a non-terminating decimal expansion of a rational number of the form p by q. Then exercise 1.4, question number 1. Without actually performing long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. Students, in this question, 10 bits are given to you, out of which I will be solving the 5 bits and the rest 5 bits are for your practice, so that you can very well understand how to solve such questions. Once again, let us move on to the question number 1, and question number 2 is related to the question number 1, that is why it's written in the along with question number 1. Without actually performing log division, we don't have to perform log division method, but we will have to find the decimal expansion also. First of all, we will have to say whether it's a terminating decimal expansion or a non-terminating decimal expansion. If it is a terminating decimal expansion, we will have to move to the second number question, that if it's a terminating decimal expansion, we will have to write down the terminating decimal expansion of the terminating decimal expansion. That means if this is a terminating decimal expansion, we will have to write its decimal form also, but without actual long division. So these two questions are related to each other. In question number 1, we will have to say whether it is a terminating decimal expansion or non-terminating repeating decimal expansion. If it is a non-terminating repeating decimal expansion, we don't have to move on to the question number 2. But if it is a terminating decimal expansion, then we will have to follow the question number 2 also, and we will also have to write its decimal form. Then let us move on. How to check whether it's a terminating decimal expansion? We have gone through 3 theorems. Theorem 1.5, Theorem 1.6 and Theorem 1.7. Basing on those theorems only, this can be solved without actually long division. Suppose which one? 13 by 3.25. If you remember the theorem, much emphasis was given on the denominator part, that is the q part, and we were finding that q part of the form 2 to the power n, 5 to the power n. If the denominator is of the form 2 to the power n, 5 to the power m, then we can say it is a terminating decimal expansion. Otherwise, it is a non-terminating repeating decimal expansion, as these are rational numbers and are expressed as p by q form. So let us emphasize on the denominator part. So let us find all the factors of the denominator, that is q. So let us find 3, 1, 2, 5. Divisible by 5, as the last digit is 5. 6, 2, 5. Again by 5. 1, 2, 5. 5. 25. 5, 4. So this can be written as 13 to the power 5, 5 to the power 4. This is 13 by 5 to the power 5. The 2 part is missing. But in our theorems, it was given that n and m are non-negative integers. That means n can take values from 0, 1, 2, 3, 4 and so on. Even m can take the values from 0, 1, 2, 3. Only the negative numbers are neglected, but it takes all the values, positive values along with 0. So here we can mention as 2 to the power 0, because the value of 2 to the power 0 is 1. Now the q part, the denominator part, is of the form 2 to the power n, 5 to the power m. So according to the theorem, we can say that it is a terminating decimal expansion. So we can write, since q is of the form Let us remove the rough cut part. Q is of the form 2 to the power n, 5 to the power n, that is 2 to the power 0, 5 to the power 5. Then it is a terminating decimal expansion. It is a terminating decimal expansion. Now since we have got 13 by 3125 as a terminating decimal expansion, then moving on from question 1 to question 2, we will have to write the decimal expanded form also, but without actual long division. So how to write that? This is 13 by 5 to the power 5. We will have to multiply. Here in our denominator we have 5 to the power 5. We have 5. This 5. We don't have here 2. So we will have to multiply 2 with the same power of the 5. Here we will have to equalize the power of 2 and 5. So what we can do is we will have to multiply here 2 to the power 5 so that we can get 5 and 2 both the forms with same powers. So if we multiply it in the denominator part, we need to multiply it on the numerator part also. This is 2 to the power 5. Now this can be written as 13 into 2 to the power 5 by applying the law of indices. This can be written as 5 into 2 to the power 5. Now this becomes 13 into 32 by 10 to the power 5. And this can be written as, if you multiply the numerator, 13 into 26, 6. 416 upon 10 to the power 5. This can be written as 0.00416. 5 decimal places as the denominator is of the form 10 to the power 5. So we need 5 decimal places. Arranging it in 5 decimal places form, this can be written as 0.00416. So this is the decimal form of 13 by 3125. This being a terminating decimal expansion can be expanded in its decimal form following this process as 0.00416. Bit 4. 15 by 1600. The method is same. We will have to emphasize on the denominator to check whether it is a terminating decimal expansion or non-terminating repeating decimal expansion. So let us convert the denominator or try to convert the denominator in the form of 2 and 5. Let us do the rough work out here. This is 1600. 2 So 50 by 1600 can be written as 1, 2, 3, 4, 5, 6, 2 to the power 6 and 5 to the power 2. Before checking that whether it's a terminating decimal expansion or not, or it's a non-terminating decimal expansion or not, first of all we will have to simplify it. If there is any cancellation in the numerator and the denominator part, we will have to cancel it, converting the P and Q into co-prime forms. Here, these are not in the co-prime forms. You can see 15 can be written as 3 into 5. And we have to cancel the common factor. So this can be written as 3 upon 2 to the power 6 and 5 to the power 1. Cancellation of 5 from numerator and denominator. And now it becomes P by Q form, where P and Q are co-primes. This we have to keep in mind, that P and Q should always be co-primes. Now, observing the denominator part, we can see that it is of the form 2 to the power n and 5 to the power n. And we have gone through the theorem that if the denominator is of the form 2 to the power n, 5 to the power n, it is a terminating decimal expansion. So we can just have to write Q is of the form 2 to the power n, 5 to the power m, that is 2 to the power 6, 5 to the power 1. So it is a terminating decimal expansion. Terminating decimal expansion. And if it is a terminating decimal expansion, as we have got for question number 1, then again the question number 2 applies, that if we are getting it as a terminating decimal expansion, we will have to write its decimal form without long division. So let us continue for writing the decimal form of this without long division. So we have 3 by 2 to the power 6 and 5 to the power 1. I have told you in the previous question also that the degree of 2 and 5, the power of 2 and 5 should be equalized. Here the highest degree of 2 is 6 and the degree of 5 is 1. That means we need 5 more 5s out here. So we need to multiply 5 to the power 5 in the denominator and 5 to the power 5 in the numerator also, in order to equalize the degrees for both 2 and 5. And this can be written as 3 into 5 to the power 5 by 2 to the power 6 into 5 to the power 6, which can be written as 5 to the power 5, that is 3125. If you multiply it with 3, this becomes 9375. So this is 9375, and this can be written as 2 into 5 whole to the power 6, which can be written as 9375 upon 10 to the power 6. That means we will have 6 decimal places, as the degree of 10 is 6. So we will have to write in decimal form 0.009375. This is the decimal expanded form of 15 by 1600, when 15 by 1600 was a terminating decimal expansion, and whose decimal expanded form is 0.009375, which we have got without actually long division. Bit 7. 129 by 2 to the power 2, 5 to the power 7, 7 to the power 5 is to be checked whether it is a terminating decimal expansion or a non-terminating repeating decimal expansion. As for the theorems that we have gone through in theorem 1.5, 1.6, 1.7, 3 theorems. Out of those 3 theorems in 1.7 we have gone through that if the denominator, that is the q part of p by q form of a rational number, is not of the form 2 to the power n, 5 to the power n, then it is a non-terminating and repeating decimal expansion. Here we observe it, we have 2 to the power n, we have 5 to the power n, and as I have told you, if apart from these 2 and 5 numbers, if we get any of the other numbers as a prime factors out here, then it is always a non-terminating decimal expansion, but it will be a repeating decimal expansion because it is a rational number, and as per the definition of the rational number, if it is a non-terminating decimal expansion, then it should be a repeating one. Here, observing the q part, if you say the q or denominator is not of the form 2 to the power n, 5 to the power m, where n, n both are non-negative integers, then the decimal expansion is a non-terminating and repeat. That means here also q is not of the form, that is the denominator is not of the form 2 to the power n, 5 to the power m, where n and m are non-negative integers, then the decimal expansion is a non-terminating and repeating decimal expansion. So here the decimal expansion of this is non-terminating and repeating decimal expansion. 6 by 15, we need to check whether it's a terminating decimal expansion or a non-terminating repeated expansion. I have told you earlier that first of all, always check that P and Q are co-prime numbers. That means they should not have any common factor other than 1. Here if we observe 6 and 15, both are the multiples of 3. That means these are not co-prime numbers. That means we will have to change the form of the rational number into P by Q form, where P and Q both will be co-primes. For that we need to simplify it. So this can be simplified as, if you cancel it by 3, this is 3 2s and 3 5s, so it becomes 2 upon 5, which can be written as 2 upon 5 to the power 1 and 2 to the power 0 in order to see. The denominator has only 5, then 2 can take the power as 0 because n, 2 to the power n. N is a non-negative integer, so it can take the value 0 also. Now the denominator becomes of the form 2 to the power n, 5 to the power m, so it is a terminating decimal expansion. So here Q is equals to 5 to the power 1, 2 to the power 0, or simply you can say Q is of the form 2 to the power n, 5 to the power n, that is 2 to the power 0, 5 to the power 1. So it is a terminating decimal expansion. It is a terminating decimal expansion. And if it is a terminating decimal expansion, then we will have to show its expanded form as per question number 2 without actual long division. So let us move on for the decimal expansion. So this is 2 upon 5 to the power 1. Now, I have told you earlier also that we need a 2 here with the same power as 5. Here 5 takes the power 1. So we need to multiply 2 with the power 1 in the denominator to get the form of 2 to the power n, 5 to the power m with the same power. So we will have to multiply it in the numerator also. So this becomes 4 upon 10 to the power 1, and this is equals to 0.4. So this is the decimal expansion of the given rational number 6 by 15, which was changed to 2 by 5 to make P and Q to be co-prime numbers. So its decimal expansion form is 0.4 because it was a terminating decimal expansion. Big 10. 77 by 210. We have to check this whether it's a terminating decimal expansion or a non-terminating repeated decimal expansion as per the question. So first of all, we have to change this in the form of P by Q with P and Q both to be co-primes. Observing the P by Q form, we can very well see that it has a common factor 7. So if you cancel it, you get 11 by 13. Now focusing on to the denominator, because the theorems were based completely on the denominator of the form 2 to the power n, 5 to the power m. So we will have to find the prime factorization of the denominator, which can be written as 11 by 2 to the power 1, 3 to the power 1 and 5 to the power 1. Observing the denominator, if we clearly see, the denominator is not of the form 2 to the power n, 5 to the power n, because there is an extra prime number which is in a multiplication form with 2 and 5, which denotes that this decimal expansion will be a non-terminating and repeating decimal expansion, because it is not, the Q is not of the form 2 to the power n, 5 to the power n. Here Q equals to 2 to the power 1 into 3 to the power 1 into 5 to the power 1 is not of the form. Is not of the form 2 to the power n, 5 to the power m, where n and m are non-negative integers. So it is a non-terminating repeating decimal expansion. Non-terminating repeating decimal expansion. Now these two questions we have done from exercise 1.4 where we have checked that without long division method, how to check whether a particular decimal expansion is a terminating decimal expansion or a non-terminating repeating decimal expansion. We have one more question in exercise 1.3, question number 3, where we have to write the P by Q form of the decimal expansion. That is, if it is a rational number, then we will have to write its P by Q form. That we have learned in class 9 also. You can refer to your class 9 book for writing that P by Q form.